All right, so let's look at how we start here on worksheet 1. It says, in discussing motion, there are three closely related concepts that you need to keep straight. And these are, here's where you start right. Position, velocity, and acceleration. So the first one, position, quite often called x of t, quite often called s of t or f of t. Doesn't really matter what we call it, okay? Quite often it's x of t for the College Board. And it determines, so the position function, which is a function of time, determines where the particle is located on the x-axis at a given time t. Now, right now, if you'll read the top of the worksheet, you'll see that we're talking about motion along the x-axis. Horizontal motion, then we're going to make it the x-axis. Okay? And that's not different than what normal functions do. It's just that normally they determine where y is. You know, you're given an x coordinate, you figure out what the y coordinate is. So you figure out what y is instead of the position. All right? So, again, this is motion along the x-axis, horizontal motion from left to right, or right to left, back and forth, left and right. Okay? Velocity can be called v of t, or whatever you named the position function, that prime. So x prime of t, or s prime of t, or v prime of t. But the velocity is the derivative of the position. The velocity function is the derivative of the position function. And this determines how fast the position is changing at a time t, as well as the direction of movement. It's the rate of change of the position. Velocity is the rate of change of the position. Now, sometimes we confuse speed with velocity. Speed is the absolute value of velocity, because velocity has a direction. And if we're talking about motion along the x-axis, a positive velocity means that the particle's moving to the right. A negative velocity means that the particle is moving to the left. And our third thing is acceleration. A of t is normally called acceleration. It is the derivative of the velocity. So it's equivalent to v prime of t. And since the velocity was the derivative of our position function, a of t is also equivalent to x double prime of t. So acceleration is the derivative of the velocity, or think of it as the second derivative of the position. And acceleration determines how fast the velocity is changing at time t. Acceleration is the rate of change of the rate of change. The sign of a of t indicates if the velocity is increasing, if a of t is positive, or decreasing, if a of t is negative. And when you finish writing, we'll talk about that. All right, now this last sentence is a fairly important one to think about. The sign of the acceleration function indicates if the velocity is increasing, and then I said if a of t is positive. All right, ignore the position function for a moment. Just think about velocity. Velocity is itself a function. If that function, if any function is increasing, isn't its derivative positive? And vice versa, if the derivative is positive, the function is increasing. So if velocity is increasing, its derivative, acceleration, is positive. If acceleration is positive, the function it's the derivative of, velocity, is increasing. And then just change it for decreasing. If the velocity is decreasing, its derivative is negative. If the acceleration is negative, the function it's the derivative of is decreasing. They should, I would still call it velocity. I would still say velocity, which is v of t equals something like that. Yeah, because I'd hate for you to miss something that you know, because, you know, like we said before, the people that we talk to on Saturdays act as if they're just dying to give you points. That's not the way I've seen them graded. Okay? I kind of see it as, you know, they don't give them away. So I would write it down. You're probably okay without it, but since you know it, write it down. All right. Now, there was really nothing new in that. It's just been a while since we've talked about velocity and acceleration. Okay? And also, a lot of times when we talked about it, we talked about objects going up and down. Right now, we're talking about objects moving along the x-axis. Okay? All right, so let's keep going here on worksheet 1. If x of t represents the position of a particle along the x-axis at any time t, then the following statements are true. Initially means when what equals 0? T. And I wrote time t. Because again, you would think anybody would know we mean t to be time. It doesn't mean anybody knows we mean t to be time. Okay? And at the origin means what equals 0? The position with the x and the y. The x and the t in this case. Or actually be the t and the x. Right? If it's x of t, t would be the independent. Okay? So x of t or s of t or f of t, but the position is at 0. Now, here's the thing. You don't have to start measuring at 0. It's most convenient to, isn't it? Okay? But, you know, you don't have to start then. You don't always start then. I mean, way back when I was young, they actually, you know, we actually knew how to fire rockets into space, unlike now when we don't know how to fire rockets into space. And we'd have a countdown, t minus 10 seconds. Okay? Now, the thing wasn't moving yet, but they were measuring the time, weren't they? With negative time. You following me? Okay? Number 3, at rest, the particle's at rest. What equals 0? The velocity. If the velocity of the particle is positive, then the particle is moving to the right. Because why? Because that's the positive direction on the x-axis. Number 5, if the velocity of the particle is blank, then the particle is moving to the left. Negative. tricky, wasn't it? They didn't just give you number 4 again and put the blank in a different spot. Okay. 6, and we may need to think about this one for a minute. To find average velocity over a time interval, divide the change in something by the change in time. Change in position. Now, what's the difference between average velocity and velocity? Velocity is really instantaneous velocity. It's the velocity at a single moment in time, whereas average velocity, average velocity can be found without calculus. Velocity has to have calculus. Fine, you could think of it that way. All right, because an average rate of change, velocity is a rate of change, still really goes back to Algebra 1, or actually pre-algebra. Yeah. Okay? So it really does. It goes back to that. Right? The second position minus the first position over the last time minus the first time. Okay? All right, number 7. It's got to put a blank. I made one up myself. I decided that instantaneous was the blank. Instantaneous velocity is the velocity of a single moment. Instant. You have to say it that way. It's got an exclamation on it. In time. All right, number 8. If the acceleration of the particle is positive, what's increasing? The velocity. Because of that function derivative relationship we always have. Number 9, if the acceleration of the particle is blank, then the velocity is decreasing. Negative, because of that same relation between the function and its derivative. Number 10. In order for a particle to change direction, what has to change, signs? Particle's going to the right. Wait a minute, that's left for you. Particle's going to the right, switches, and goes to the left. What had to have happened? The velocity had to equal 0 for a moment, correct? So the velocity went from being positive when the particle was moving to the right to negative when the particle was moving to the left. It had to equal 0 in between, or vice versa. Maybe it was negative because it was moving to the left and then switched to positive because the object then moves to the right. So don't forget that a direction change, and this is not just velocity, is it? If you've got a graph, all right, for a graph to change from increasing to decreasing, its derivative has to change from positive to negative. Okay? And number 11. One way to determine total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all resting points. Now let's stop and think about that for a minute. If you've got a particle, there's the x-axis, and it starts here, and it moves here, and then it moves here, and then 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 when you stop, it's right back where it started. Its total distance traveled is not 0. Its change in position is 0. But its total distance traveled is not 0. So, how do we account for that? Well, we can measure the distance traveled from where it starts to where it goes to rest. And then measure the distance traveled from rest till it rests again. Then measure the distance traveled from rest till it rests again. Now, you might say, but what if it rests and then keeps going the same direction? It still works, right? From where it starts to where it rests, measure that distance. From where it starts to where it rests, measure that distance. From where it starts to where it rests, measure that distance. Don't we still get the total distance? Now, we did more work than was necessary. If it never changes direction, we can just measure the ending position minus the beginning position, and that's the total distance. But if we don't know whether or not it's changed direction, our first method will work, won't it? Okay? So, here's an example. If the position of a particle is given by, and then here's our position function, x of t equals 1/3 t cubed minus t squared minus 3t plus 4. Find the total distance traveled on the interval from 0 to 6, including 0 and 6, which is important in this case because we need to know that t equals 0 matters and t equals 6 matters. All right, so my question for you, how do we find where the resting points, as they call them, are going to be? Where the derivative, the velocity, equals 0. Okay? So, here we go. Find the resting points where the velocity, which is x prime of t, and I wrote sideways just to make it fit on my paper because I was at the bottom of the page. As you know, I usually go down the paper, and you can too if you've got room. So when the velocity, which is the derivative of x of t, which is, and this is an easy derivative to take, t squared minus 2t minus 3, which is also factored as the quantity t minus 3 times the quantity t plus 1, equals 0. So we find the resting points by setting the velocity equal to 0. And then I got two solutions. I got t equals -1 and t equals 3, and I crossed out the t equals -1. Why did I do that? Because the interval they give us is from 0 to 6. Now, pay attention to context. In most cases, regardless of my countdown example I gave a minute ago, does time being negative make a lot of sense in most contexts? In most contexts, no. Could there be a context where it does? Well, yeah. I mean, for some reason, if you wanted to, you could start your stopwatch at -10 and go from there. You could do that. Okay? So, in fact, it makes you look really good at track. Yeah, I would suggest that to Coach Box. Just for your race. Started at -10, you'll be setting world records. Easy. All right. So, now we know the resting point. We still, though, have to find the distance traveled. All right, so we start at 0, we rest at 3, so then we start again at 3, and we end at 6. So now, find the position at the resting point and at the end points. That way we can measure the distance from 0 traveled from 0 to 3 and from 3 to 6. All right, so x of 0 when time 0. In other words, we're finding the initial position of our object, aren't we? When time t equals 0, so I put a 0 back here in our original x of t function, and I get 4. So x of 0 equals 4. So the starting position wasn't 0, it was 4. Yeah, it would. So now let's find the position when the object comes to rest. So let's find x of 3. So you plug in a 3 for the t in the original x of t. I got -5. Anybody else get -5? Everybody just going to nod and smile because I said it was -5? Okay. X of 3 is negative 5. The position when t equals 3 is negative 5. How far has it moved so far? 9. And then find its final position, x of 6. So I'll put a 6 in there for t. I get 22. Does anybody else get 22? 2200? I'm not sure. All right, so the particle moved 9 to the left. Okay, 27. I must have messed up. It moved 22 to the right, right? Exactly. It did move 27 to the right because it starts at negative 5, ends at 22. That's moving 27 to the right. Okay, so 9 to the left, 27 to the right, for a total distance traveled of 9 plus 27, 36. Now, we don't know what 36 feet, 36 miles, 36 units, whatever the unit of measurement is. All right. And now we take a look at worksheet 2. Now, worksheet 2 has, we're looking at motion numerically in example 1, graphically in example 2, and analytically in example 3. The AP people are really big on you being able to figure all this out, right? They want you to be able to crunch the numbers analytically. They want you to know what the graph looks like, and they like tables. So that's what the numerical is. They like tables. The older I get, the more I do calculus, the more I see value in tables. Because the more I realize that that's the way the real world works, right? When you're observing data, when you're observing, in this case, motion, you probably don't know that x of t equals 1/3 t cubed minus whatever that other worksheet 1 problem was. But you can measure how long it takes to travel 9 to the left and how long it takes to travel 26. You can do that. You can make a table out of it. Okay? So, tables are big. And I think they're just going to keep getting more important as you go through your math life. But here in example 1. The data in the table below gives selected values for the velocity in meters per minute of a particle moving along the x-axis. The velocity v is a differentiable function of time. If it's differentiable, what else must it be? Continuous. Now, continuous functions aren't always differentiable everywhere. That's that cusp thing. All right? That function is continuous, but it's not differentiable right there. But the converse is true. If a function is differentiable, it's continuous. So maybe that's going to be a big deal. Maybe it doesn't come into play, but there's probably a reason they told us. Okay? Not necessarily. They could just be messing with us. But there's probably a reason. So look at the table they give us. The table, up here we have our times in minutes, and then down below we have the velocities in meters per minute. Okay? So, question number 1. At t equals 0, is the particle moving to the left, or to the right, or to the left? And they want us to explain. So look at t equals 0. What's the velocity at t equals 0? -3. Okay, so this is moving, and it's moving to the left. So at t equals 0, the particle is moving to the left. Why? Because it says explain, because the velocity is negative. Not because it's -3, but because it's negative. All right, number 2. Is there a time during the interval from 0 minutes to 12 minutes when the particle is at rest? I don't see any zero velocities. Yeah, if velocity is differentiable, we've decided that means it's continuous. If it's continuous, if it's negative sometimes and positive sometimes, it's got to cross zero. Okay? So yes, and I'm writing more down than would be required as a test answer. But I want you to understand this. So you write down as much as you need for you to understand it. Okay? So yes, the particle must be at rest to change direction. Since velocity is negative at t equals 0 and positive at t equals 2, the particle changed from moving left to moving right. 4. And be careful, too. I probably should have said, and is therefore at rest, because, you know, they want us to use the terms they use. Or, think about it this way. Since velocity is a differentiable function that was given to us, it is also continuous. So, and here's another thing they like, right? We had a session on this on one of those Saturdays. So, the intermediate value theorem states that since the velocity goes from negative to positive, it must go through 0. In other words, that v of t equals 0. And if you forget the name of the intermediate value theorem, what do? Just write the theorem out. Just write your explanation without stating the theorem. So do both of those ways make sense to you? Are they essentially the same explanation? I think so. The second one I threw in, if I hadn't thrown in the intermediate value theorem, the fancy name, wouldn't it be essentially the same explanation? Okay? Number 2 makes sense? Good. Number 3. Use the data from the table to find an approximation for v prime of t and explain the meaning of v prime of t in terms of the motion of the particle. Show the computations that lead to your answer and indicate units of measurement. I don't know why they tell us to approximate it. I'm just going to look in the table and, whoops. They don't give us that. They don't tell us, you know, there's not a column right here, time t, velocity equals whatever, all right? But if there were, that's where it would go, right? So, does that give you any clues how we might approximate the velocity at time t? Find the average velocity, or the average, wait a minute, I'm saying the words wrong. They want the approximation of v prime of t. So find the average rate of change of the velocity. So scratch what I said. I said velocity when I meant rate of change of velocity. Okay? So find the average rate of change of the velocity, which is essentially the slope formula. So v prime of t is the rate of change of velocity at t equals 10. So I explained the mean prime of t first. V prime of t is the at that particular time t equals 10. We can approximate this by the rate of change of velocity as near to t equals 10 as we have data for, or data to use. There will be something like this on the AP test, where you have to approximate a derivative of a table of values by finding the average rate of change. Guaranteed. Over the year, there's been a lot of things I've guaranteed are going to be on the test, hasn't there? A lot of things on the test. Yeah, there's even numbers on some of them. All right, so v prime of t is going to be approximately, all right, y2 minus y1, so v12 minus v8 minus x2 minus x1, 12 minus 8. Now, this is me explaining to you more than it is me thinking you have to write this on your answer. That's the change in velocity divided by the change in time. And then you just get the information from the table. All right, it's 5 minus 7 over 12 minus 8. That's negative 2 over 4. That's negative 1/2. Now, writing this explanation out does help me get the units right, because velocity would be in meters per minute, and then acceleration, see what the denominator was when we found the average acceleration, right, which is the average rate of change of the velocity, average acceleration. It's change in time, so it's also in minutes. That's the reason when you give acceleration in your science classes, it's in, feet per second squared or feet per second per second. Okay, that's how that works out. So this is in meters per minute per minute. Okay? So v prime of t is approximately negative 1/2 meters per minute squared. And that is the approximate acceleration at time t equals 10 minutes. Now, have I been redundant with my naming things and writing things down? Yes, I have. Hopefully that helps you understand it. You don't have to be redundant on the test. You just have to be accurate the first time. Okay? All right, about out of time. Number 4. Let a of t denote the acceleration of the particle at time t. Is there guaranteed to be a time t equals c in the interval from 0 to 12 such that the acceleration at that time equals 0? All right, I've answered it 2 different ways. I'll talk fast. You can write at your leisure. Yes, since the velocity is differentiable and therefore continuous on the interval from 6 to 12, and v of 6 equals v of 12, then Rolle's theorem states that there's at least one number in that interval such that the derivative of the function v prime of c, which is a of c, equals 0. So good old Rolle and his theorem. Or, yes, since v of t is differentiable and therefore continuous on the interval from 6 to 12, then there exists a number c in the interval from 6 to 12 such that the velocity, which is the acceleration, equals, and then remember the mean value theorem was that the slope of a tangent had to equal a slope of the secant. That's what that is. So the slope of the tangent, v prime of c, equals the slope of the secant, v of minus v of 6 over 12 6, which in turn equals 0. So the velocity equals 0 by the mean value theorem. And a little extra learning. If we knew that v prime of t equals a of t was continuous, and since we know v of t increases then decreases, that is, that v prime of t is positive, then on the interval from 0 to 12, then the intermediate value theorem would guarantee at least one number from 0 to 12, where the v prime, the derivative, equals 0. Now, go back and get this off the video if you have to, but get that in your notes because it's getting close to test time. You need to be remembering Rolle's theorem, mean value theorem, and intermediate value theorem again. Not the name so much as what they do.